Alright, so let's talk today about section 4.3 and 4.4 at the same time. In these sections we're going to talk about logarithmic functions, which I abbreviate log functions, and their graphs. So one thing that's probably good to remind ourselves of before we start is, let's recall this about graphs and inverses. So let's say I had a graph that looked like so. Let's call this the point 1, comma 2, and we'll call this 3, comma 5, and we'll call this negative 3, comma 2, say for example. Okay, so let's say this is our function. I would know what the inverse function would look like, even if I don't know the equation of the inverse function, because what I would need to have is a flip-flop of the points. So for example, if I have 3, comma 5 up here, well, first of all, we know because of this flip-flopping of inverses in their graphs, here's the line y equals x, and whatever I shape that I draw upon here, the inverse needs to be symmetric with respect to the line y equals x. Okay. So instead of having the point 1, comma 2, the inverse function is going to have a point 2, comma 1. And also, instead of having the point negative 3, 2, I'm going to have 2, comma negative 3. So I know those will be there. I also will have the point 5, comma 3. And so while I don't know what the equation of this graph is, I know that this is the inverse, because I've flip-flopped the points. Okay. It all comes back to, remember, our diagram. Okay. Say I have a set of numbers, and this will be the domain. Okay. And this is the domain of f. Okay. I'll take some element in there, we'll call it x. Okay. And when I put x through our function, out comes another element called y, and this is in the range of f. But I'd really like to know, how do I undo what has happened to x? So that is, if I'm given a y, can I put y in and come back with x? And that can happen as long as I put it into f inverse of x. And so now these set of numbers have become the domain of f inverse. And these set of numbers, which were the domain of f, are now the range of f inverse. Okay? Alright. So this is a very powerful tool, okay, to help us think about what's happening with functions and their inverses. Okay. So let's go back to what we were talking about last time. We were talking about the exponential function. And let's recall what we did. Okay. So a basic exponential function, let's say we're graphing f of x is equal to 2 to the x. We saw then that every exponential function has the y-intercept of 0, 1, because anything to the 0 power is just 1. We saw that it took off exponentially as x got larger than 0. And then as x went to negative infinity, the graph approached our horizontal asymptote, which is the line y equals 0. Okay, so this is f of x is equal to 2 to the x. We know that if x is 1, then we have 2. If x is 2, we have 4. If x is 3, 2 cubed is 8, etc. If x was negative 1, we got 1/2. If x was negative 2, we got positive 1/4. Okay, so these values kept getting closer and closer to 0, staying positive, but never approaching 0. So I would like to know about the inverse of this function. It is a 1-to-1 function. It passes the horizontal line test. So its function exists and is a function. So let's put in our line y equals x. And let's just think about what would have to be, what the graph would have to look like. Okay. Well, maybe right before we do that, let's just review just a little bit more. So we have the exponential function 2 to the x has a y-intercept of 0, 1. It is 1-to-1. It has a domain of all real numbers. There's no value of x that I can't put in. The range, on the other hand, the lowest value that I can pick up is 0, but it'll never equal 0, so I have to put a parenthesis around it, and the highest value we can take on is infinity. So we have a y-intercept of 0, 1. Ordered pair, not an interval. And as an x-intercept, there is none. Direct result of the horizontal asymptote and also the range. So there is no x-intercept. Right. Now let's think about what this inverse should look like. Well, if I flip-flop the points, I know that I have to have this point 1, 0 on there. I also have to have the point 2, 1. I also have to have the point 4, 2, 8, 3. Okay. I could draw that shape in because I'm following symmetry with the line y equals x. So the question is, what's happening in between 0 and 1? Well, I need to have the point 1/2, negative 1. I also need to have the point 1/4, negative 2. And I could go further. I would need to have the point 1/8, negative 3. And so the graph would have to look like this. But now, instead of having a horizontal asymptote, I would have to have a vertical asymptote, which I would draw in. That vertical asymptote is the y-axis, and the equation of the y-axis is x equals 0. And so this would have to be f inverse. So let's think about these same questions. Now, what is the domain? Well, reading from the graph, the lowest value of x I can pick up is 0, but it's an asymptote, so I can't include 0. And then the largest value of x we can include is infinity. The range, the lowest value of y that we can pick up, starts at negative infinity and will continue to positive infinity. So the range is all real numbers. And notice the domain of f is the range of f inverse. And the range of f is the domain of f inverse. So it follows the mapping that we drew here. If we ask about a y-intercept now, that is, where will this graph cross the x-axis, the y-axis, and we have a vertical asymptote there, so it will never touch the y-axis, so there is no y-intercept. If we ask about an x-intercept, though, this certainly does exist, and it is the point 1, 0. So again, these two are flip-flopped from each other. And we could also ask ourselves about, is this function one-to-one? And if we pass horizontal lines through, it will pass the horizontal line test, and so yes, this is also a one-to-one function. So this function exists. It is the inverse function, and it is denoted as the log, and then I put a little subscript here, of 2, because the base was 2, and then the argument is of x. Okay. Now, as a direct result of this domain, whatever we put in here, x must be positive. So you can't take the square root of a negative number. You also cannot take the log of a negative number. So let's see if we can answer these questions. Now, what is the limit as x goes to infinity of the log base 2 of x? So as I'm letting x go to infinity, what is happening to the function? Well, the function is taking off to positive infinity. I could also ask about this notation. I could ask about the limit as x goes to 0 from the right. So here's 0. I want to be to the right of it. And so what's happening as I approach 0 from the right? So as I approach 0 from the right, the function is diving. That is, the limit as x approaches 0 from the right of the log base 2 of x is equal to negative infinity. So these are some characteristics about 2 to the x and its inverse, the log base 2 to the x. So I should give you a definition. If we have some function which is equal to a to the x, okay, a could be 2, 3, 4, anything but 1. If we have that, then f inverse of x is equal to the log, and you put whatever base is here, of x. And vice versa. So if your function is this log base a of x, then the inverse, that is, what will undo it, is a to the x. So they are inverses of one another. So we'll have to be comfortable with those. There's also another, so we need to get very comfortable with this. What we could do then is give you one more definition, because if we are given a logarithmic form, we can always write it exponentially and vice versa. So let's say if we have y is equal to some log base a of x, then we can write a to the y is equal to x. And this goes both ways. Okay? So if you have this, you can write that. If you have that, you can write this. They're equivalent statements. This is an if and only if symbol. It means if you have this, you can go here, back and forth freely. So what does that mean? All right, let's talk about the log form. So here, I could have the log base 5 of 25 is equal to 2. Okay, let's say I have that. Then I can write that exponentially. And what this is saying is that the base 5 raised to the second power equals 25, which is true. We also could say, like I had a log form of log base 2 of 1 over 16 is equal to negative 4. Well, exponentially, this is saying 2 to the negative 4 power is equal to 1 over 16, which is true. Remember, 2 to the negative 4 is 1 over 2 to the positive 4, which is 1 over 16. Here's another. The log base 1/3 of 9 is equal to negative 2. So exponentially speaking, I take the base 1/3, and if I raise it to the negative 2 power, I should get 9, which is also true. Okay. 1/3 to the negative 2 is the same thing as taking the reciprocal and now raising it to the positive power, which is 9. So we're going to have to remember our rules of exponents. If I have the log base 36 of 6 equals 1/2. This is the log form of me saying 36 to the 1/2 power is equal to 6. And it's also true, we have to remember that 36 to the 1/2 power is the square root of 36, which is 6. And then things we have to watch out for, like say we're taking the log base 5 of negative 10. This will not be a real number. Can you think of why that would be? It's because, now this is the log base 5, and I'm showing you the log base 2, but all of these basic logarithmic functions have the same shape and the same characteristics, and the domain is that you can only put in positive numbers. 0 won't even work. So here, I'm trying to take the logarithm of a negative number, and that doesn't exist in the reals. So that's some more about logarithms. Let's transform some of their graphs for a little more practice and we'll come back. Okay, so let's say, for example, that we had the log base 2 of x minus 4. Okay. So we saw from before that the logarithm, this had an asymptote. This is the equation of the asymptote x equals 0. We had an x-intercept of 0, 1. The graph took off to infinity and approached the asymptote. Okay. And this was the log base 2 of x. So a transformation of this function, notice that as I've drawn it as a quick sketch, I've drawn two important things. I have drawn the x-intercept, I have drawn the equation of the asymptote, and then I guess the third important thing is I drew the correct shape. So what we're now looking at is how this x minus 4 affects it. And remember, using large, since I am subtracting, I must be moving right. So everything has to move right 4 units. So now, instead of being at 1, 0, I have an asymptote, an x-intercept at 5, 0. Okay, so 1 plus 4 is 5. But then this asymptote also has to move over 4 units. So we'll come here. So now this is the equation x equals 4. And then the shape must stay the same. Then we can ask questions. What is the domain of our transformed function? Well, our transformed function is in green, and the lowest value x picks up is 4, but it's not included because of the asymptote, and then it continues to infinity. The range, on the other hand, will stay the same. It will still go from negative infinity all the way up to positive infinity. I could also then look at what if I had our function be f of x is the log base 2 of x minus 4 minus 3. So this first part is our green graph, but now I'm going to subtract 3, so this entire graph needs to shift down 3 units. So instead of having our important point be 5, 0, it will shift down to 5, negative 3. The vertical asymptote will also shift down 3 units, but it's an infinite line, so it will not change. So, kind of drawn this. So it will stay the equation of x equals 4. And now the graph can be drawn like so. So now the domain has not changed. It stays from 4 to infinity, and the range has not changed. And these will be the transformations. There will not be a y-intercept, because if we let x equal 0, we'd take the logarithm base 2 of negative 4, and that's not a real number. We could ask about this point. This is our x-intercept. So what will happen when we take the log base 2 of x minus 4 minus 3 and set it equal to 0. Well, let's isolate this logarithm. This would be the log base 2 of x minus 4 is equal to 3. And then I could write this exponentially. I could say, well, 2 cubed equals x minus 4. Or that 8 is equal to x minus 4. So x is equal to, adding 4 is 12. So this would be the point 12, 0. And this would be our x-intercept. So that's transformations. Let's try and do some other types of special logs.